Hey everyone, and welcome to the Explainer! I am absolutely thrilled to guide you through today's topic. We're going to dive right in and unlock the secrets of geometry, taking you from the most basic fundamental triangle rules all the way to completely mastering complex n-sided shape formulas and proportional scaling. If you've ever looked at a massive polygon or a really tricky similarity problem and felt, well, a little overwhelmed, don't worry. By the time we wrap up this explainer, you're going to see these concepts not as a bunch of random equations to memorize, but as a really beautiful, logical system of building blocks. In fact, these are the exact same building blocks video game designers use to render entire virtual worlds. Here's a quick look at our roadmap for today. First, the mighty triangle. Second, quadrilaterals and basic polygons. Third, the interior angle formula. Fourth, the 360-degree exterior rule. And finally, section 5, rules of similar shapes. Let's get right to it. Okay, if there's literally only one number you take away from the first half of this explainer, let it be this one, 180. It's the most important number in basic polygon geometry. Why? Well, because the interior angles of every single flat triangle in existence, whether it's long and skinny, a perfect equilateral, or a right-angled wedge, always add up to exactly 180 degrees. This is our master key, right here. Everything we do with larger shapes is really just borrowing this exact 180-degree rule. Now check this out. Notice how extending one side of a triangle outward creates an exterior angle? It perfectly connects the inside of the triangle to the outside. Our source material gives us this brilliant little shortcut. That exterior angle is exactly equal to the sum of the two interior angles on the opposite side. So instead of wasting time calculating supplementary angles on a straight line, you can just add those two opposite inner angles together. It's an elegant mathematical shortcut that'll save you so much time. Before we start stacking our 180-degree triangles to build bigger shapes, let's get our terms straight. A regular polygon is a closed two-dimensional shape, but here's the crucial part. All its sides are of equal length and all its angles are of equal size. Think of a perfect square or a standard stop sign. When you see the word regular pop up in a geometry problem, you should honestly breathe a sigh of relief. It means perfect symmetry. Whatever the total angle sum is, we know we can just divide it evenly among all the corners. Let's quickly look at how the names build up based on the number of sides, and by extension, the number of angles. 3 is a triangle, 4 is a quadrilateral. But look at the progression from 5 onwards. Pentagon for 5, hexagon for 6, heptagon with 7, octagon with 8, nonagon with 9, decagon with 10, and skipping down to 12, we have the dodecagon. Getting comfortable with these prefixes is super important, because problems will often just say a regular nonagon and expect you to instantly know, right, n equals 9. All right, let's start stacking those building blocks. If you draw a straight line from one corner of a rectangle across to the opposite corner, just a simple diagonal, what did you just do? You didn't just draw a line. You actually proved that a quadrilateral is really just two triangles stuck together back to back. Every single four-sided shape can be perfectly split into two three-sided shapes. And that brilliantly illustrates our next rule. Since we just proved any quadrilateral is made of exactly two triangles, and we already know every triangle holds 180 degrees inside it, well, the math just kind of does itself. 2 triangles times 180 degrees equals 360 degrees. So the sum of the interior angles of any quadrilateral must absolutely be 360 degrees. So the really cool part is that we can apply this logic to any shape, no matter how many sides it has. Here's the step-by-step breakdown. Step 1, count the number of sides, which we call n. Step 2, pick one corner and draw lines to all the other corners to see how many triangles fit inside. You'll find it's always the number of sides minus 2. For example, an 8-sided shape, you can fit 6 triangles inside it. Step 3, since every triangle is 180 degrees, you just multiply that number of triangles by 180. Which brings us perfectly to the formal mathematical way of writing what we just figured out, the interior angle formula. 180 times n minus 2. Now, I don't want you to just memorize this as some random sequence of numbers and letters. I want you to see the hidden geometry working behind the scenes. That n minus 2 is literally just the number of hidden triangles locked inside the shape. Multiply that by 180 degrees, and boom, you've got the total interior degrees of the entire polygon. Let's actually walk through how this works with a regular pentagon. A pentagon has 5 sides, right? So n equals 5. Plug that into our formula. 5 minus 2 is 3. That means we have 3 hidden triangles inside. Multiply 3 by 180, and we get a total of 540 degrees. Now remember our definition of a regular polygon? Because it's regular, all 5 corners are identical. So we just take our total, 540, and divide it by 5. That tells us that every single inside angle of a regular pentagon is exactly 108 degrees. This perfect, stable symmetry is exactly why the famous U.S. Department of Defense building was designed in this exact shape.
Pretty cool, right?
Now let's step outside the shape for a minute. What happens if we extend the sides of the polygon outward to create exterior angles? Well, our source material gives us one of the most unbreakable, wonderfully simple rules in all of mathematics. The sum of the exterior angles of any convex polygon is always 360 degrees. Seriously, it doesn't matter if it's a triangle, a pentagon, or a massive 100-sided shape. If you walk all the way around the outside of a shape, making a turn at every single corner, you are going to turn exactly one full circle, 360 degrees. Because that total is always locked at 360, finding just one exterior angle for a regular polygon is incredibly straightforward. Step 1, start with 360. Step 2, divide by the number of sides, n. And that's literally it. If you've got a regular hexagon with 6 sides, you just divide 360 by 6. That means every single exterior angle is exactly 60 degrees. Okay, let's do a quick challenge. Let's reverse engineer the rule we just learned. If I tell you that every exterior angle of a regular polygon is 15 degrees, can you figure out how many sides the polygon has? Take a second to think about the formula we just used. And here's the answer. Because we know the total of all the exterior angles must be exactly 360, we just take that 360 and divide it by that single angle of 15 degrees. 360 divided by 15 equals 24. So this shape has 24 sides. What initially looks like a really complex, abstract geometry problem gets solved in about 5 seconds when you know the unbreakable rule of the outside circle. All right, shifting gears here, we're moving from angle properties to proportional scaling, also known as similarity. We are officially leaving the world of fixed angle sums and stepping into the fascinating realm of magnification. Basically, how do shapes behave when we blow them up or shrink them down? To really grasp this, we need to define exactly what similarity means in geometry. 2 polygons are considered similar if they meet 2 strict conditions. First, they must be equiangular, which just means all their corresponding angles are exactly the same size. Second, their corresponding sides must be in proportion. Now, what's really interesting is that for triangles, just having the same angles is enough. If a tiny triangle and a giant triangle have the exact same angles, they are mathematically guaranteed to be similar. When you're dealing with similar shapes, the most important tool in your toolkit is the scale factor, which we represent with the letter K. The scale factor is simply the ratio of the side lengths. Let's say a side on your small shape is 2 centimeters and the corresponding side on the big shape is 6 centimeters. Your scale factor K is 3. The shape is 3 times bigger, and this rule applies to all linear measurements, side lengths, perimeters, and even the vertical heights of the shapes. But here is exactly where people get tripped up. Look at the clear comparison here. On one side, you have your standard scale factor, K. This is strictly for one-dimensional measurements, length, width, height, perimeter. We're just talking about lines. But on the other side, the area factor. Area is 2-dimensional, right? It's length times width. Therefore, the scale factor for the area must also be squared. It is K squared. Let me really drive this point home, because it is absolutely crucial. The area of a similar shape is magnified by the square of the scale factor. If you take a triangle and you double the length of all its sides, you haven't just doubled its area. No way. Your scale factor K is 2, so your area factor is 2 squared, which is 4. By doubling the sides, you have actually quadrupled the amount of physical space inside that shape. If you triple the sides, the area gets 9 times bigger. It's a massive magnification that you always have to account for. And that brings us to our final takeaway. Just look at what we've unpacked today. You now hold the 3 master keys: 180 degrees to unlock those inner triangles, 360 degrees to circle the exterior, and K squared to accurately magnify area. Geometry isn't about memorizing 100 disconnected rules. It's about seeing how everything naturally connects back to these foundational truths. So my challenge to you is this. The next time you face a complex polygon or a tricky scaling question, don't panic. Adapt your style. Find the hidden triangles, check the outside circle, and pinpoint your scale factor. You've got the tools to break it down. Thanks so much for hanging out with me today on The Explainer, and keep exploring the geometry all around you.